Hello, dear friends. Today we are introducing to you electronics. This is going to be a very important channel for you in the areas of electronics, embedded systems, tech. That is an area to deal with app development and many others. So, to begin with is a discussion on a very important device called capacitors, and this is very paramount in the design of analog electronics. So electronics engineering is brought to you this lecture, and you can reach out to us via these links and those contacts. So let's look at capacitors in a real life. So majority of the capacitors available outside there, you'll find them looking like this. At least you have one of this kind that you have met outside there. Now, what is a capacitor? It's just an electronic component that stores energy in an electric field. Yes, capacitors store electrical energy in electric fields. The key components, they consist of two conductive plates, usually metal separated by small distance, and even an insulating material called a dielectric is placed in between the plates. Usually we use mica and other insulators. So the analogy that we can use in order to understand a capacitor, think of a capacitor as a tiny temporary battery that can store and release energy very quickly. Imagine a very small battery that stores a given amount of energy and releases it quickly or discharges quickly. So that can be compared with a capacitor. So how does it work? When voltage is applied, one plate accumulates a positive charge and the other accumulates a negative charge. So the dielectric prevents the charges from moving between the plates, creating an electric field. So you have charges on one side, a negative on one side, and another positive on the other side. And this creates what we call an electric field. So the capacitor is charged when it holds this electric field. When it maintains this electric field, that's when we say the capacitor is charged. It will hold the charge until a path is created for electrons to flow, at which point it now becomes discharged, or it is going to discharge away this energy. So let's look at the capacitor formula. The capacitor has a measurement that we call capacitance and is capital C, measured in farads, and is defined as the amount of charge stored per unit of voltage. So the capacitance is defined as the amount of charge stored per unit of voltage. So meaning if we wanted the capacitance, this would be the amount of charge Q divided by voltage. So let's look at an example. A circuit contains a 10-volt battery connected in series to a 2 microfarad capacitor. After the capacitor is fully charged, how much charge is stored on its plates? So we have 10 volts and then the capacitance is 2 microfarads. So this is micro is times 10 to the power negative 6. So 2 times 10 to the power negative 6 farads. So meaning we use the formula. First of all, Q is equal to CV, and therefore we are able to determine the charge. So we know that C is in farads, that is the capacitance, V is in voltage, Q is coulombs. And therefore we have 10 volts and 2 times 10 to the power negative 6 farads, or 2 microfarads. So applying that in our formula, Q is equal to CV, then we'll have 20 micro coulombs as the charge that is gonna stored between the plates when we have 10 volts across the plates, and the capacitance of the capacitor is 2 microfarads. Yes, so let's look at the common types of capacitors. So one is electrolytic capacitors, and these are characterized by high performance polarized. Okay, they are polarized, therefore they must be connected in the correct direction. Should you make errors, then you're going to cause fires. And they are often used for filtering power supplies. The appearance is typically cylindrical. And when you look at such a capacitor, this is an electrolytic. And looking at the legs of this capacitor, the longer one is positive and the shorter one is negative. Therefore, this is positive, this is negative. Yeah, types of capacitance. So under electrolytic capacitors, we have what we call tantalum capacitors. So this is an electrolytic capacitor subtype, and they are composed of tantalum metal, which serves as an anode, a layer of oxide that serves as a dielectric, and a conductive cathode. Tantalum capacitors are generally polarized, which means they can only be connected to a DC supply if the terminal polarity is correct. So if you have a correct polarity, that's only and only if you can connect them to a DC supply, meaning a negative must be connected to a negative terminal and the positive terminal must be connected to the positive terminal. So that is how the tantalum capacitors, one of them looks like. So the disadvantage of using tantalum is that their unfavorable failure mode. They have unfavorable failure mode, which can result in thermal runaways, fires, and small explosions. Yes, so now, having looked at this problem, we can be able to solve or avoid it by using external fail-safe devices such as current limiters or thermal fuses. They are nowadays found in various circuits, including laptops, automotive industry, cell phones, and others, most commonly used as surface mount devices. So, because of taking up less surface, the surface mount tantalum capacitors, you'll find them, they are used in most of the PCBs or printed circuit board, and this allows higher packing densities for the PCBs. So the next type is ceramic capacitors, and these have low capacitance, they are non-polarized, and are great for high frequency circuits. The appearance is that they are small, you can see, are disc shaped, they can also be rectangular. They are of low cost and high speed switching capacitors, commonly used for noise filtering, for tuning of circuits, coupling, and other applications. They can also be found in resistor capacitor, inductor capacitor, and resistor inductor capacitor filters. These ceramic capacitors can switch faster than electrolytic capacitors. However, they are not available in high capacitance values. So you can see a 22 picofarad ceramic capacitor. An example is here, and this is 22 times 10 power negative 12 farads. So the next type is called the film capacitors, and these have good stability, tolerance, and they are suitable for timing and high power applications. Their appearance is usually rectangular or oval, so you can look at them, and the applications of capacitors, okay, Having looked at a number of capacitors, ladies and gentlemen, we can look at the applications of these capacitors. So one of them is filtering or smoothing of signals. Usually this is in power supplies. So they are used in power supplies to smooth out the pulsating DC voltage, converting it into a steady and clean voltage. Capacitor can fill in the gaps of a bumpy DC signal. So you can look at this bumpy DC signal and you'll see that this difference is actually what constitutes the ripple component of voltage. So this is the DC output, but remember we need the DC that is smooth. So to smoothen out these vibrations or alterations, then we use a capacitor to fill up with this. So at one point is charging, at another point is discharging, and to make sure that it fills out these gaps so that what comes out is a smooth power signal. Another application is that we use these capacitors in timing. So because capacitors always charge and discharge, and therefore this time in which they discharge and charge is predictable using a time constant that is equivalent to the resistance times capacitor. So we know that the capacitor takes some time to get fully charged and to fully discharge. This property can be used for the timing circuit design. If we control the charging and discharging time of the capacitor, it can therefore act as a timing circuit. So another application is in energy storage or flash photography. In a camera flash, a large capacitor is slowly charged by a small battery. When the photo is taken, the capacitor releases its stored energy almost instantly, providing the bright flash of light. So you can see here, this capacitor is the one that powers the flash mechanism for this camera. Yeah, so let's look at the behavior of capacitors in circuits. With a DC source, a capacitor behaves as if it is an open circuit. Once it is charged and is fully charged, it can no longer take on anything. Therefore, when it is fully charged, it acts as an open circuit. Now, capacitors store energy in an electric field, and their charging stroke discharging speed in a DC is determined by a time constant RC, which is the product of the circuit's resistance and capacitor's capacitance. Let's look at the alternating current. How does it affect capacitors? So a capacitor acts like a short circuit or a pass-through for AC signals. It continuously charges and discharges, allowing the AC current to flow through. In the case of AC, the frequency is finite, hence the value of reactance is finite. Thus, the AC current to flow through it. We can look at this formula. The capacitance, the capacitive reactance of a capacitor is Xc, and is always equal to 1 out of omega C, whereby omega is 2 pi f, and then C is the capacitance. So when we compute this, we find that Xc is a resistance in ohms, and you see this F is possible only and only if we have AC. With the DC, F is 0, and that's why we find that at some point Xc becomes infinite. It is too big. Therefore, the capacitor will be seeing an infinite resistance and therefore cannot pass on current from one side to the other. So what are the key takeaways? We have the capacitor stores electrical energy in an electric field. Its capacitance is a measure of its ability to store energy. The common types include electrolytic, ceramic, and film. And capacitors are used for filtering, timing, and energy storage. They even block DC but pass AC. Ladies and gentlemen, capacitors are a cornerstone of modern electronics, essential for everything from power supplies to mobile phones. Thank you so much. Remember to subscribe to Herotronics so that you don't miss any video in embedded systems and other tech related concepts and subjects. Thank you.